All right, good morning, everyone. Um, so I sent you an email earlier today asking you for you to already create the GitHub workflow for this next exercise. So I asked you to call that 09 open data, and then of course do the whole process of starting on GitHub, making a clone of that on your local computer, creating the subfolders code data output. Then on the 2024 DSA, doing a git pull, getting the new data and partial script, move that to the appropriate folders here. So I am hoping that you were all able to make it to this point where on your the main folder of the course, you have the 09 open data project with the R project there with the code, which would be the 0321 Daymet partial, and also the data called fielddata.csv that I share with you. All right, so given that, and given that we ran out of time last class, I have a quiz for you all. So the quiz, the goal of that quiz was to have given it to you at the end of last class, but because we ran out of time and did not want to keep you for longer, so we're going to have that today. If you go on your ELC, let's see here. I think you can all, I think it's already visible for you. It's called quiz 3 iteration. If someone can confirm to me that it is visible to you. Okay, so I'm just gonna give you here 5 minutes for you to complete. So it's not a very difficult or long quiz. So let me just put a timer for 5 minutes. At the end of that, I'm going to close the quiz. So make sure you submit your answers before the 5 minutes end, because after that point, I'm going to close it. And then we're going to start out with the class. We have a quiz that's ending in 3 minutes, 40 seconds. If you can make it in time, you're welcome to. Otherwise, I guess you're going to have to miss it. It's on ELC. Last minute here. Last 10 seconds. Make sure to submit your answers. I'm going to be closing the quiz here shortly. All right, time's up. I'm going to close it now. Make sure you submit like right now if you haven't yet. All right, so quiz is closed. Let's we're going to talk about it next class. We'll go through the answers. I think I already got the answers after you submitted, but we can talk about them in more detail next class. Okay, so for today's exercise then, assuming you already are set up, let's go ahead and launch our project here. So the 09 open data, and get started with this exercise. So please go ahead and make sure you launch the script. And I just want to give you some background here on what we're going to be doing today and how that's going to fit into our overall class objectives. So there are many open source databases that we can pull from, especially here in the US. The US government collects a lot of data, makes a lot of data available that can be really important for creating machine learning workflows and analysis. To have that type of data already available, you just have to be able to find it and download it. So some of these databases one of the strengths of them is that they can be from a large scale. So let's say you can pull data from anywhere in the US, you can pull data from anywhere in the globe, really depending on the source. And they're also really useful because not just they have this spatial extent that's very large, but they also have, depending on the data source, you may also have an archive of data, right? So you can go back in time and really see like, okay, so I had this study that happened, last year. Can I still find data that could be useful for that study? So if you go into some of these sources, you're going to find an archive that may go back many years in the past that will allow you to have some of this data, even if you had not planned originally to use it. So really this like temporal and spatial availability of data can be really important depending on the project. So some of these may be related to crop. So for example, USDA National Agricultural Statistical Service, USDA NASS, has really so much data about different crops. I think the finest spatial scale they go is at the county level. So you can download data at the county level for many different variables. For example, planted area, harvested area, yield, production of any crop that's of importance for a given state. You can download that data related to crops. Also soils, there are different soils databases that we can pull from. If you're taking, I know some of you are taking my other class, we pull data from Sergo, which is one of the databases for soils, but there are others that are also available. There's one that's called Soils Grid. That's a soils data set that is available for the whole world, really. So really a lot of good resources here for soils as well. Today, we're going to be pulling weather data. So that's going to be our goal here. We're going to be using a source called Daymet. We're going to talk about that in a second here. But weather data, there are different sources as well that can be used depending where you are in the world. Daymet is one of them. Also remote sensing. So Landsat, Sentinel, even planet data, planet scope are some of the sources that we can pull remote sensing data for a given field, keep track of a crop's growth, and perhaps, even finding treatment effects and differences in your field based on remote sensing. And again, the beauty of it is that it can go back in time and look at that archive of data that is really important. We can also get elevation data. So if you're playing at a field scale, where you're planning a study, or maybe you're trying to understand the effects of elevation, slope, and aspect on yield, we can also pull that open source data and really many other variables. These are some of the most common examples here that I wanted to share with you. And why are these important? So imagine that so it happened to me in a data set that I am partially sharing with you for this exercise. We have access to this database here that is related to a study that has been conducted since 1980 until present day across the US. So we have the location of the studies, and we have something that was measured on the field. So this is normally what you would do most of the time, is you would go there and collecting the ground truth data, right? So that could be yield, it could be some disease incidents, it could be crop quality, perhaps different aspects that you go to the field and you actually measure. That is the bottleneck. That is the most limiting data that we can have in a machine learning workflow, is to actually have the ground truth data that you are all collecting for a research, most likely. But now we can connect whatever you're measuring on the field with a whole bunch of these complementary layers that we can pull from open source data. Of course, the best type of data is the one that you collect. So if you have, for example, a weather station right next to a field, that's going to be the best weather data you're going to have. If you can go to a field and pull soil samples that you know geospatially where they came from, that is the best type of soil data you can get. However, if you did not do that, and that happened in the past, you cannot go back and do it. We have these sources of data here that I want to share with you, at least one example today for us to go through. So really the learning objectives of today are going to be to learn about and implement the download and pre-processing of a spatial and temporal weather open source database. This is going to be Daymet. Daymet is a database for weather that is a predicted database for weather. So they do use data coming from different stations, but they create an even continuous layer of weather data that starts in 1980 till present day. It has a temporal resolution of daily. So if you go today, you're going to find data all the way from 1980 until yesterday on a daily scale, and provides you a handful of weather variables at that scale. And it has a spatial resolution of 1 kilometer, if I remember well. I think I have that note here. So really imagine that at every 1 by 1 kilometer pixel across the whole US, you're going to get daily weather data that you can pull from. And again, open source, free data. So we're going to be exploring that. We're going to pull weather data for multiple sites and years for the data set that I share with you. And then we're going to export it to file, because we still need to do some feature engineering, which is going to happen in the next class. So I hope that you are seeing, I guess, this flow of, okay, we have this data that was collected from the field, which we're going to talk about in a second here. We are pulling one open source database, in this case, weather, to bring all these potential predictor variables to be used in a machine learning model. And then next class, we're going to do some wrangling and also some feature engineering, which is basically creating new variables based on the ones that we get from the database. So that's going to be our steps for this week here before we actually are ready to get into the machine learning side of things. So I left you here this first chunk. I have a few packages that I left you to comment off and install. So maybe let's do this. Go ahead and first, if you don't have these packages yet, first install the Daymet R package. This is the one that's going to give us access to the open source database for Daymet. So install that one first. Just push like command return or just run that line of code. You don't have to run the whole chunk at this point. Once that goes through, and if I remember from when I installed this, I think it was pretty straightforward. If there are any issues, let me know. So this really is the package that we need to pull data that we're going to be using today. The other packages here, so I have two more packages that I want to install. One is SF. This is basically a package in R for us to deal with vector geospatial data. This class here is not about geospatial data, so I'm not going to get into a lot of detail here. If you're taking my PrecisionLab class, we talk a lot about this package and how to use it in different ways. For this class here, that's not the main goal. I just want you to install so we can visualize this data in space. So please go ahead and install the package SF. I think it should be straightforward. It may ask you to install other dependencies as well. If it does that, you can just say yes. And I think it should be straightforward as well. And if someone that is installing it can let me know how that's going, just so I have a feeling of if my assumption of it being straightforward is working. Okay, perfect. So SF is going to help us to create maps of, let's say, points and polygons. If that doesn't make sense to you now, don't worry. You're not going to need to know that a lot for this course. It's just for us to visualize the data that we're going to import. There's also this other two packages called USA Boundaries and USA Boundaries Data that we need to install from GitHub. For us to install a package from GitHub instead of CRAN, so if you remember, CRAN is the official R archive or repository for packages. If we are basically think of it as we are skipping the App Store that CRAN is, we're going straight to GitHub to install these packages. To do that, we need to use another package that allows us to install a package from GitHub. That other package is called remotes. So you may need to install the package remotes first, and then you can comment that off, and then you can run one at a time, these two lines here, to install the packages USA Boundaries and USA Boundaries Data. These two packages, again, are geospatial in nature. What they're going to give to us is an easy way to retrieve state and county political boundaries and use them for creating maps in R. I think that if you install both of those, you should be good. I remember from my other class when we were going through them, maybe there were some messages there. If anyone runs into issues installing these two packages, let me know. What is it saying?
No package. Added in load namespace. And then there is no package called remote.
Did you run the install packages remotes first? Yeah, so run that first, and then the other two. Is there any difference on installing them for either CRAN or GitHub? So Kriti is asking if there's a difference from installing them from CRAN or GitHub. I think that these packages, Kriti, are just available for GitHub. So what happens normally when someone is developing a package, if they want it to be like widely distributed through CRAN, they have to submit that package through CRAN. So maybe the package is, most of these packages are on GitHub anyways, but if you submit it to CRAN, then CRAN has a whole bunch of checks in place to make sure a package is running properly, is safe, and so on. It's almost like, you know, submitting an app to App Store or having that outside of the App Store. You know, if it goes through the App Store, which CRAN would be the equivalent here, it has been through some checks, and it's more warranted to work and do what it's supposed to do. But you don't have to have your package submitted to CRAN. And sometimes people do have a package that is submitted to CRAN, but they also have a GitHub version. Normally, the GitHub version would be the most up to date because it's so easy for them to update. For the authors to update on GitHub, and then only at a given frequency, they would submit that version to CRAN. So normally, if a package is in both places, GitHub would be the most up to date, most likely. My install package SF is taking a long time. Is that expected? Did anyone else install SF today and is running for some time? Okay, so Austin, no one else here seems to be having that issue. What I would say is look into your console. So sometimes like on the console, it may ask you like, for you to install this package, you may need to push 1 to update other packages or to say yes or no. So maybe it is taking longer, not because it's actually running, but because it's waiting for you to give an answer on the console. So take a look at the console. Yep.
From the time you said to go ahead and like run it, it was running and it finally just started on, or it finally finished. So I don't know why it took so long, but it took a tremendous amount of time.
Okay, interesting.
But it did just finish.
Okay,
Ironically.
nice. All right, so I guess we can, well, anyone else have any issues installing any of these packages here? All right, so I'm just gonna comment off from my side so I don't happen to accidentally install them again. And then we can load the packages here. So we're loading tidyverse, which again is that meta package that has many other packages inside of it, all part of the tidyverse, including ggplot, dplyr, and others. We're loading USA boundaries. So this is the one that, again, we're gonna use just to retrieve the state political boundaries to make a map. We're gonna load SF, which stands for simple feature. So we can actually create the map itself. And then the package Daymet R, which is the one that's gonna give us access to the open source data from Daymet. Okay, so just wanna give a quick moment here and ask if anyone had issues when loading the packages. Because if you had issues installing, then you would see that issue as well when you try to load. All right, so don't hear anything, so let's keep going. So the first thing I want to do here in this chunk that I want to ask you to code with me is just to import the data that I share with you. And I want to assign the data to this object called field. So if you just use the assignment symbol, that is a CSV file. So we're going to use read_CSV. We get outside of the code folder by .. hit tab, go inside of data, hit tab again. It should bring the field data.csv. As you bring that, it should appear on your environment. And let's just take a look at what this data set is. So this data here, it's about 700 observations. So we see it has 700 rows and 5 columns. It's about 700 observations that include year. So this is when the study was conducted. What was the site? So this is the site name that includes city and state. It has a lat and a long column. These are latitude and longitude. These are geospatial coordinates, right? So these are the coordinates of where the trials happen. And then we have our explanatory variable or predicted variable of strength in grams per text. So what this is, let me give you more background on what this study here is. So this is a study that has been conducted through different state cotton specialists across the cotton belt, which spans from Georgia all the way to California, from 1980 to 2020. So the data spans that much time. The goal of this study was to measure cotton fiber quality and yield in different sites and different years as well. This was actually a variety trial, meaning that on each one of those locations, there were, I don't know, 10, 15, 20 varieties. I'm not giving you all that data. What I did here is get us the mean cotton fiber strength at a given site year. So we're basically ignoring the effect of variety. We're just looking into that spatial and temporal aspect of the data. So here again, the columns are year, so that's the year that the study was conducted. Site is the location of that study that includes both the city name and the state. We have the latitude and longitude columns. These are in degrees. So these, if you go on Google Maps and you drop a pin, you're going to find your location in longitude and latitude. It's just a way of locating things in the globe. And then we have our actual variable of interest, which is the strength in grams per tex. So this is just a measure. So imagine that they had these trials. It was a variety trial. They had a whole bunch of varieties. They collected samples from these varieties, got a measure of yield, sent these fiber samples to a lab to get quality analysis done. Fiber strength is one of those quality parameters. So it's basically how much of grams per tex it takes to break the cotton fiber, the cotton fiber sample of that analysis. So it's just a number that the higher this is, normally the better it is, right? So in cotton production, growers get paid not only based on yield, but also on quality, where strength is one of the quality parameters. And in this case here, the stronger is the fiber, the better price the grower gets paid. So in our exercise here, our goal is to understand what are the main weather drivers of cotton fiber quality. And for that, again, we have 700 site years that we have data from that we're going to be using to train this model. All right, so let's just quickly explore this database. So we'll do some exploratory data analysis as always, and just try to understand a little bit better what this data set here has for us. So if you run the next chunk, is just a summary of the variables. Really, I guess the most interesting one is strength by itself, as that is our only predictor or predicted variable or response variable. So it's ranging from 19.67 grams per tex to 37.94 grams per tex. This just gives us some idea of this distribution of this variable. But so some other questions that if this was the first time I was seeing this data, I would have some other questions before I started even plotting or doing anything with it. So one of them would be, okay, I know I have 700 rows on this data set, or 698 rows, where each row is a combination of a year and a site, right? So one question that I would ask myself is how many unique years I have in this data set, right? So that's the first thing that I want us to explore here. I want to ask, I know that we've done some wrangling throughout different exercises, but I don't know if we've done this specific type enough, but what function would you need here to find out that number? What did you say, Renisa? Distinct, right? I would use that one as well. And maybe there are different ways of doing this, but definitely distinct is what I would use. So we can start with the object name here, that is field. I just want to give a distinct. And really, so if we give distinct here, it's probably going to return the same number of rows, because really each row here is unique. There's no duplication of year in site that's appearing more than once in this data set. So if I want to know how many unique years, we can say distinct year. So just distinct on that year column. So if we do this, it gives us back just the distinct number of years. So we see here starting in 1980 and going all the way to 2020. And we have a total of 41 rows here, meaning that we have 41 distinct years in this data set, right? So again, from 1980 to 2020. Awesome. All right, so what if then I want to know how many unique sites? It's the same idea, right? So we're just going to call field, give it a pipe, and then ask for distinct. But now we need to specify another column, which is going to be the site column, right? So distinct site is going to give us how many and which ones are the distinct sites of this data set. So after doing that, we see we have 60 or 65 unique distinct sites in this data set. And we can really see here, I mean, if you wanted to see all the names, you could just browse through this list here. But as we're gonna see shortly, there are sites that go all the way from Georgia or from Georgia all the way to California across the southern states of the US, which are the states that grow cotton. All right, so the next thing here is I want to take a look at the statistical distribution of fiber strength, and I want to do this in a plot manner. So I'm gonna start off here with a ggplot, where I'm gonna say data equals to that object, so data equals to field. And I'm gonna already go ahead and put strength on the x-axis. So I'm gonna say x equals to, if you just print field below, so you get the name of the columns. So x equals to strength g-tex, or grams per tex. All right, so if I just do this and we'll run it, I just give us that empty canvas because we have not added any geom yet. So if I want to look into a statistical distribution of this data, there may be a few ways in ggplot that we can do it, but there is one that we've been using most of the time when we look at these. Anyone has a thought? Come on. Okay, we could use box plot. We can go ahead. So, well, let me say that we could use box plots, but that is not exactly what I want to show here. Any other thoughts? Density, right? So box plot and density are similar, but density gives you more information about it. So let's put density here. Yeah, Kriti said geom density as well. That's where I was going. Thanks, Kriti. So if we just say geom density, he actually did not work. Oh, you know what? I forgot to put the X on the inside of AES. So remember that. So AES and the X goes inside of that. Yes, thanks, Sikar. Yeah, I was forgetting the AES here. So if we put that, it should work now. All right. So, and just to make it clear, so Pramod said box plot. That could also be, we could also use box plot. What I've seen is that sometimes a box plot distribution can, like the box plot itself can look very similar when the density or the histogram look different. So different densities and histograms can create a very similar looking box plot. So box plot is good, but when you have a lot of data like we have here, I think a density was more descriptive of that shape. So that's why I went for it, but box plot would also work here. So here what is happening, and as you notice, so with geom density, really we give a variable on the x-axis and we do not give anything on the y-axis, because the density is going to basically be, this is almost like the outline of a histogram. So imagine a histogram would be bars under this outline here. So density is almost doing that for us. And notice how we only gave the x variable, right? So the reason for that is the geom density is a special type of geom that actually calculates the y-axis for you. So the y-axis is an outcome and not necessarily a variable in your data set. So we did not have a column saying density, right? Density was calculated by geom density for us, and it's just placing that on the y-axis. So the way that we will look at this is strength is on the x-axis. We see that, probably the mean is around 30, I would say, looking at this distribution, and we have values ranging from 19 through 30, or I don't know, this is going to be, so 38 perhaps, right? So just looking at this distribution, it looks, the raw data here looks fairly normal, but remember, normally we don't make a lot of assumptions based on raw data. Those assumptions, at least of the linear models, are based on residuals, but it's still, but just looking at the raw data, it looks fairly normal. All right, so what I have on the next chunk here is actually, I wanted to create a map. So my goal next is gonna be to create a map of the entire US with the state boundaries and place the dot of these trials on where that trial is coming from. So if you remember, our data frame here, field, has a lat and long coordinates. These would be the points in space where those trials happened. So I want to create a map of those points, but I also want to have in the background the state boundaries for all the contiguous US states. So that's what we're going to do next in this chunk here. The first thing that we want to do is create an object that is going to contain the state boundaries of the US. So that's going to be the first thing. I want to call that object states. Give the assignment symbol. I want to use this function here that comes from that USA boundaries package. The function is called US_states. So if you just run that, I think it should work. And if you print states, it's going to print a little bit differently. If you have never worked with simple feature or SF objects in R, this is going to look different to you. If you have been working with these or familiar with them, then this would look familiar as well. So what this is telling us is that it has 52 features. So each feature here would be a row in this data set. And the geometry type is multi-polygon. That's because each state is a polygon, right? So it has like a boundary. You can think of that as a polygon. And then it shows us here the data. So here are the columns. So state FP, state ENS, a whole bunch of things here. It has a column for name of the state. It has a column for, it even has a proportion of land, proportion of water, and other things here. But really, one of the main differences between an ASF object and just a regular data frame is that an ASF object has a geometry column, that is the last one here, that carries the geospatial information of those polygons, of those states. Again, we're not going to talk a lot about this here, but I just wanted to give you some background of what this is and what we're doing. All right, so right now, what I want to do here with you is start plotting. We're going to run into some issues, and then we're going to solve those issues and plot again. So this object states, we can give that as a data frame to ggplot. So let's go ahead and start our ggplot right below it. So ggplot, you can leave it empty at that level. Ggplot, we're not going to be providing the data right there. Here return, and because so this object states is an object of class SF in R. These types of objects are treated differently in ggplot, where they have their own geom. So the geom for that is called geom_SF, where all we need to say is just data equals to, and then the data set. We don't need to say anything else. As you run that, it's going to create for you a geospatial map of all the US states, or territories, right? So we see the contiguous states, we see Alaska, this is Hawaii, this is Puerto Rico, I believe. And I don't even remember what is this. Oh, I think this is just part of Alaska, actually. It's just like going out on the other side of the globe, but it's still Alaska. So really, for this map to look a little bit nicer, I only want the 48 contiguous states. So to fix that, we just come here back to this states object. If I print again states, it has a column for name, and it also has a column for state abbreviation. So state ABBR. So we're going to do a filter here where we're going to remove those states that are not part of the 48 contiguous states. We're going to do that based on this state abbreviation. So if you think about it, there are 52 states or territories here in this list, and I want to keep 48. It's going to be easier to say which ones I don't want to keep, which are just 3. rather than saying the 48 I want to keep, right? So let's do that. If you just add a pipe, we're gonna call the function filter. I don't remember if we've been through this approach here in previous exercises, but what we're gonna do first is say, filter those three states, and then we're gonna come back and negate that, meaning only do not filter these three. So to begin with, let's only filter those three states. I want to use this column here, state ABBR, for state abbreviation. So I want to filter state ABBR. If I only have one state I wanted to filter, I could say equals, let's say PR for Puerto Rico. I could do this. In this case, it would only filter Puerto Rico. However, I have three states. Every time you have more than one thing that you want to filter in or out, we need to, instead of using equal sign, we need to say percent and percent. And then we give on the, as part of the C function, we give those values. So it would be filter state in the C function where PR is the first state abbreviation. The second one is for Alaska, which is AK. The third one is for Hawaii, which is HI. And then make sure you close the last parenthesis there, because now we have a parenthesis for C and a parenthesis for filter. If you run that and you just print states, now it only has three features, which are those three that we filtered, right? However, I want to filter them, but filter out and not in. For us to basically like negate all this statement, so get the opposite of that, what we do is you just, so right after filter parentheses, you add an exclamation point, and then you open parentheses and close the last one. So I'm basically saying, take this state abbreviation in PRAKHI and then do the opposite of that, which is what we get when you do that exclamation point in the beginning. So you get the opposite of that. So if you do that, and now you run it, you run the ggplot, you should end up with only the 48 contiguous plots or state maps. All right, so this is part of what I wanted to show you. Now, the next thing that I want to do here is put a dot on each location that we had a trial. So we're going to come here on this next, on the ggplot, add a plus. Now, if you are taking my other class, or maybe if you've been working with SF objects, maybe our approach here would be to first transform this field into an SF object, which is what we would do if we were doing more geospatial type of analysis. In our case, we're not going to do that. So this field here is going to remain as a data frame and not as an SF object. Because it is a data frame, we cannot use geom_sf. So we're just going to use geom points, because we just want to make points where those coordinates are. So let's add a plus. Let's call it geom point here. We're going to say data equals to field. Right, so if you print field again, this is what it looks like. It is a tibble, it is a data frame. On the AES, so open AES, we're going to say x equals to long. So long is for longitude. Longitude is that degree in the x-axis, and then comma y equals lat. If you just run that, then we get this plot. So each one of those dots is where we have at least 1 year of trial for that given location, right? Let me just leave this a little bit longer in case anyone's catching up. So what we can see here, first off, is we have most of these points here, or all of these points here in the southern part of the US, which are the states that grow cotton, right? There's very little cotton. There's going to be very little cotton as you move north from those states that we have points being represented. We see here in Georgia, there's data from 3 locations. It looks like this one here is Midville. This one here is probably Tifton. I don't know really where this one is. I don't know, maybe it is Watkinsville, but it looks like a little bit too far to the west to be Watkinsville. But But anyways, Georgia has three sites where these trials were conducted, and that data was contributed to this data set. All right, so before we go to the Daymet part of it, any questions about until this point, what we've done and what we are finding out? Yes,
Like I'm trying to hear you remove my other that too.
it did not. So if you were not able to remove the other states, I would say, first off, make sure you're filtering the right column, right? So you want it to be state ABBR for abbreviation. Make sure you're using the percent in percent. Make sure your acronyms are uppercase, as that is how it's written in the data set. Make sure that you then wrap all this in quotation, in parentheses, and then you have your exclamation point right before that. You have all that in place and it's still not working? Okay, let me come and take a quick look here and see. All right. Okay, so let's talk about Daymet a little bit. So Daymet is an open source weather data that is developed by NASA. I'm leaving you here the link so you can explore on your own if you wish. And this is just a excerpt that I got from that website that it says Daymet provides long-term continuous gridded estimates of daily weather and climatology variables by interpolating and extrapolating ground-based observations through statistical modeling techniques. So basically, it is a continuous layer that they have all these weather stations on the ground collecting data, and they use that along with remote sensing and other models to extrapolate those data into space and have a continuous layer to be used. Some of the data characteristics I wanted to share with you about Daymet, and this is going to be important for you every time you're looking at open source data. You want to check 4 main things here. One is going to be the spatial extent. So where does that open source data cover in space? In the case of Daymet, it is for North America. That includes USA, Canada, and Mexico. What is the spatial resolution? So how big is the pixel size that information is coming to you? In the case of Daymet, it is 1 kilometer. There are other weather open source databases that are coarser than this, meaning that the pixel may be like 4.6 kilometers by 4.6 kilometers in size, or even larger than that. Daymet is probably the finest one that you're going to find for weather, and especially in the US. Next is the temporal resolution. So this is how frequently you get new data. For Daymet, it is daily. So every day there's a new layer across North America with different weather variables at 1 by 1 kilometer spatial resolution. And also the temporal extent of it. So Daymet begins providing data in 1980 and it ends yesterday, whatever day yesterday would be. And then the variables that it gives you are these. So day length, precipitation, shortwave radiation, snow water equivalent, max and mean air temperature, and water vapor pressure. So if you have any studies, even the ones that happened in the past, where they have maybe you have multiple sites and you happen to not have a weather station near them, you could go back in this archive here, go back in time, pull weather data for the whole growing season, as long as you know the spatial coordinate of where that field was and when your studies happened. Right, so you can always go back in time and retrieve data from the past. All right, so this is it's an open source database, so it is hosted in a server somewhere and is updated by someone. But then how do we get access to this? So a lot of these open source databases have application programming interfaces or APIs. You probably heard of the term API already. So API is just a connecting point between their data and them making that data available to a user, right? And that user can use that API to connect with a database through different ways. Sometimes this API is going to be through your web browser. Most of the time, they do provide a programming way for you to bring that into, your local machine or maybe even the clouds. So in our case, that API to Daymet is going to be through the package called Daymeter, which is the one that you downloaded or installed today. The main function that we're going to use to connect with this database is called download Daymet. And I just want to get the help of that function just so we look into the documentation and understand what we need to have and to give the function to get back weather data. So if we look here, this function has the following arguments: site, let, long, start, end, and then some other things here. So really, what we're going to need to give it, the most important pieces are let and long, which we already have in our data set. We already have those columns. And start and end, if we go into the arguments and understand what that is just the start and end of the year that you want that data for. So you're not going to say, I want data from this day to this day. You're going to say, I want data for this year, and you're going to get data for all days of that year. And then if you do want, you can then filter after that point. Right, so we need just to give like the start and end year, which is going to be the same for a given site year, and then the longitude and latitude. And we already have all those in our database, right? In our data set, our field data set, we already have all those columns there. So it's going to be pretty straightforward to just go ahead and pull that data. All right, so let's try pulling Daymet data for the first site year in our data set. So for one of the 698 site years in our data sets. So if you, I just left field there for us to print below so we can take a look at it, right, in the name of the columns. And what we're going to do now on this Daymet1 object is where we want to use that function and pull and assign to this object all the weather values for this first site here. So we're going to give the assignment symbol and call the function that's the name of the function is download Daymet. That's the function that we just saw the documentation of. And so it has, let's go one by one on the arguments here. So it has the argument site, right, where I want the site to be this first value here. So for us to get this first value, we're just going to give the name of the object. So that is field. And then we use $sign to get to that column. So that column is the column called site. And we just use double brackets and the number 1 there to sample that first number right there, or that first value right there. So if you were just to run field $sign site bracket 1, you would get Altus, Oklahoma. Right. So that's what we're giving it. It's just, we're going to be giving pretty much all of the first row of data for this function download Daymet. All right, so site was the first argument. Let's give it a comma and break code so we can see a little bit easier. The next argument here is going to be lat. That's the latitude of that site. Again, if I just want to give the latitude of that first site, we're going to call field $sign lat bracket 1. If I just print field $sign lat bracket 1, we get the latitude of that first site. Right, so I just got that number up there. We're going to do the same here for long. So there is an argument called long. So longitude is going to be equals to field $sign long bracket 1. Next is going to be the year. So the name of that argument is start. So I wanted to start on that first year there on this data frame, which is 1980. So just for us to keep here with the programmatic way of getting that value, we call field $year, bracket 1. So that should return to us 1980. And then lastly, we do call the end argument, which is the ending year, which is really going to be the same as the start year. So you can just copy that from above, or if you want to type, you can also do that. And one last argument I want to change here is one called simplify. So I just want to come here to the documentation again. So the argument simplify is going to output tidy data. Every time we can get tidy data out of anything, that's a plus. And for some reason, the default here is false. Or actually, it says it is true. Maybe changed. But anyways, let's just make sure we have simplify equals to true. So it comes in a tidy format as much as possible. All right, so now if you run this function, it just made an API call for the database of Daymet, and it's telling us that downloading Daymet data for the location that you gave the name, the latitude and longitude, and so on. Now, if you just print this object Daymet1, this is what we see. So the value of site, well, I guess to begin with, it has 2,555 rows in 9 columns. It has a site column, a tile column. So the tile would basically be what was the tile from the Daymet database that it found this location to be in. What was the latitude and longitude, was the same value all the way down. What is the altitude of the field? And then it gives you the year. And here are the 3 main columns that it gives you that are really the most important ones. So it's giving this column Y day, which basically ranges from 1 to 365. That is the day of the year, right? It gives you this column called measurement. So on measurement is going to give you all the variables that is pulling from this database, but is doing that on a long format. So if you remember, we talked about pivot long, pivot wider. Here, it's almost like instead of having a column for each one of the other variables, it just has one column with all the names of those other variables and another column with their values. So that's why we have so many rows in this database, 2,555. All right, so one thing that I want to show you here in the next chunk is normally we want each column to be a variable. That is normally the format we want our data sets. And right now, especially the weather variables here are not that way, right? The weather variables are under this column, which if you browse enough here, so the first one is day length. The second one, scroll through, is going to be precipitation and so on. So all those weather variable names are under this column measurements. All the values are under the value column. So on the next chunk here, I want to change that from a long format to a wide format. What function do we need here? Pivot wider, right? So let's give it a pipe. Let's call pivot wider. So there are 2 arguments we need to give here. So one is the argument names from. So the name of the new columns, where are they under right now? So right now, the name of the new columns after we pivot wider are under this column called measurement. So we say names from measurements, give it a comma, and then it has another argument called values from. So values are going to come from the current column called value, right? So values from equals to value. So if you run that, all right, let's look at what happened here. So now we have 365 rows because each row is for a given day of the year for that year that we pulled the data from. And now look at how each one of the weather variables now became their own column, right? So we have all those that we said earlier for day length, precipitation, solar radiation. SWE is snow water equivalent. So if you have snow and you want to know the equivalent of that in water, if you're doing water balance, that's an important source. Then you have Tmax and Tmean for temperature, and then vapor pressure deficit. Or vapor pressure, just I guess, that's the name of the variable. Water vapor pressure, yeah. All right, so this is starting to look like something that we could use, right? So now we have all these variables on a daily scale for one of the side years, right? Now, what if I want to do the same thing for the remaining 697 side years? This is where the reason why we had the iteration exercise first. So we would first understand some ways of doing iterations. So we talked about creating functions, using for loops, using list mapping with the per package. So now we're actually going to apply this, apply all this, all that we learned on the previous exercise to downloading all the data, weather data for all these side years. So what I'm proposing here is that we use the function map from the per package. So that was the last, well, it was the list mapping approach we did. So if you remember from the previous class, we use map when we have just one iterating variable. We use map2 when we have two iterating variables, and then we use pmap when we have multiple iterating variables. And actually, I guess here I'm saying map family of functions, but really we're going to need to use pmap in this case. So this part of the exercise here, I want to do a very quick change on the go and give extra credit if someone can do this before I show you how to do it. So I want to come here and create a new chunk where I want to, let's do this. Let's, if you all can help me here. So let's call this object extra cred. I want to start with field. So field is our data that we have here. And I want to just take the first 5 rows. So let's use the function slice and start at 1:5. So it only takes the 5 first rows. So if you print extra cred, you only have 5 rows of data. All right. What I want to ask you to do is to create another chunk here. And let's call this Daymet underscore extra cred. I want you to use a pmap function, create the code for a pmap function, and assign that on this object. So we're going to start here with your extra cred object, add a pipe, and then the rest is up to you. So here's what I want to propose. If you have people around you, if you are in a classroom with other people, partner with someone working in doubles. I'm not gonna give you a lot of time. It's gonna be, let's start with 5 minutes and see. So this is gonna be extra credit. If you cannot do it, that's okay. You don't have to worry about it. If you can do it, I want to give you extra credit. And the reason why I want you to work in doubles is because one of you may open the previous exercise and look at that pmap code that we had there and try to understand what would be the equivalent of applying that pmap in this case. A quick help here is that inside of a pmap, you're going to have to call the function download underscore daymet. And each one of these values here is going to have to come from the mapping side of it, right? So if you remember on pmap, you create the placeholder first, placeholder terms first, and then you call them in the function. So here inside of saying field $site1, you would actually call, let's say, .site, where .site was one of the placeholders that you created on the pmap level. All right, so partner up with someone. I'm going to open a GitHub. So if you get this to work on your side, so if you can get this object Daymet extra cred working, all I wanted to do is to copy this code and paste on a GitHub issue I'm going to open right now. And I don't need to see you working on your side, because if I look at the code, I'm gonna know if it's working or not. So all I need you to do is, if you get this to work in the next 5 minutes, post your code in this GitHub issue I'm gonna open right now. And then we're gonna go from there. If you got it right, then you got extra credit points. If you did not get it right, you're not gonna get hurt by that. It's not gonna be, not gonna lose points. All right, so partner up, get started. We're gonna have 5 minutes and I'm gonna open the GitHub issue here. You know where to go? All right, we're coming to the last minute here. All right, so time is up. I think we only got one person or two people submitted. Nice. All right. Perfect. So really, again, my goal here was to get you thinking about these in a way and trying to understand. I only gave you the first 5 rows because now we're gonna write the code for the all 698 sites, which may take a little while. Actually, I think maybe in class, we're still gonna do a slice and not do all of them. And then I'll ask you to run that on your side after the class is done. Just so we don't sit here, I don't know, for 5 minutes just waiting for the code to run. All right, so I will go through your answers afterwards. For those of you who submitted the answers, and I'll check to make sure they work on my side once I copy and paste them. So let's go ahead and develop the code of how we would do this for our actual full data set. So I want you to come to this chunk here called Daymet all. I'm gonna give the assignment. We're gonna start with field. I will, again here, I will do a slice for the first 5 rows. Again, just for time's sake, I don't want us to be sitting here 5 minutes waiting for this to download. But after the class ends and before our next class period, I do want to ask you to run without the slice so you get this done applied for all fields. So let's go ahead and slice again, 1 through 5, just so we get only the first 5 rows. I just want to print that to make sure it worked. All right. Let's give it a pipe here. So map, map2, and pmap, we need to use them inside of a mutate, right? So we're gonna call here mutate. I want to call this column here weather. It could be called whatever, right? I'm just calling weather because that's going to be weather data. And now because we're going to be always outside. Because we're going to be iterating over. So imagine that for each one of these rows here, I want to have a new column that's going to be called weather, where for each cell of that new column, we're going to have a data frame, right? Which would be exactly as this data frame here that we had for one of the examples, right? So that's what I want to happen here. So let's call pmap. We're using pmap here because we're going to give this function, let's see, year, site, latitude, and longitude. So 4 values we're going to give to this pmap function. So we have to specify 4 columns. Therefore, pmap is what we need here. So if you had a chance to look at the previous code, the way that this starts is we give it a list where we specify the name of the placeholder that we want to have and associate that with the current column name. So the values that I'm proposing here could be and will likely be different from the ones if you submitted an answer or if you're thinking about this, they're going to be different. That doesn't matter, right? As long as you keep consistent within what you're doing. So the way I want to call this is I want to call .y equals year. So just to remind you, year is a column in the data frame. I want to be the placeholder for that to be called .y. Again, the .y could be named something else, is up to you. Would have been up to you. So I give it a comma. The next one is the site. I want to call this .site to be the placeholder, and that is equal to the column called site. Give it a comma. The next one I want to call .lat as the placeholder name to be equal to the column called let, comma, lastly, dot long is going to be the placeholder for the long column. Right, so this is where we define in a list the association between placeholder names and the actual column names. I want to make sure I break code here where it makes sense for us to be able to read this a little bit easier. So after we close the list, but not closing the PMAP yet, if you just have your cursor going back and forth around that parentheses, you can see what is the closing, what is the opening parentheses that parentheses is closing. So right there, I want to give it a comma, we'll hit return. Here we're gonna basically call this function, that is called function. And we're just gonna call the name of the placeholders. So .y, comma, .site, comma, .let, comma, .long. After here, we break code again to make it a little bit more easy to read. And we call the function name, right? So the function, in the case of PMAP, we do not need the tilde. If it were map or map2, we would use a tilde before the function. In this case here, PMAP, don't need the tilde. We're just gonna call Daymet, or I'm sorry, not Daymet, download _Daymet. That's the name of the function that we need here. I want to break the code after the parentheses again, just to make it a little bit easier to read. So the name of the arguments here are site. So site's going to be equal to .site. Then we give it a comma. The next one is going to be let. So the argument let is going to be equal to .let, which is our placeholder. There's an argument called lon, which is the longitude, that's going to be equal to our placeholder .lon. You give a comma. The next argument is start. So we're going to say start equals to .y. That's the placeholder for the year that we're using. Give it a comma. It has also the argument end, which is the ending year, which is going to be the same as the starting year. So .y as well. And then there are a couple of more arguments I want to change here. So if we give it a comma, one of them is simplify. I want to say simplify equals true. It seems like that is the default, but maybe it was not in the past. So just to keep making sure that it is simplified and tidy, we say simplify equals true. And then once you run this on your side, here's what I would say. So give it a comma. It has this argument called silent, which is the default is false. Let's say silent equals true. What that does here, and this is an argument that you would find in the documentation of the function. We did not see this earlier, but I do want to do that here because once you start doing this for 698 sites, for each one that downloads is going to give you a message, which is really not that useful because, you know, it's just telling you that it downloaded data for a given site and year, which is this message, the same as we got on the first. Whenever we pull this one first here, we got that message. If you don't want to see that same message 698 times, silent equals true, silence that. And then one more thing here. Well, I guess we can go ahead and run this. It was not going to take a lot of time. So let's just, if you make sure that you got all of your parentheses and commas right, this should work. So I think it worked. I did not get any errors. Just went through. So now we can just print Daymet all. So it's still 5 rows because we sliced in the beginning, but now you have this weather column, right? So this weather column is, the name is weather because that's how we named on the mutate. And basically each cell here is a full data frame from Daymet for that site year and location. So let's quickly inspect here the first data set. So this first position right there. So to do that, the name of the object that we assign all this is Daymet all. So let's do Daymet all $weather bracket 1. So we get the first data set in that first position and look into it. So if you run that, it is basically the same as we got when we ran just for one site. The first example we did, right? So one thing that you don't know yet that is going to be a problem, but I want to anticipate is that right now in the nested data sets, which are all the cells under weather, we have a column called site and a column called year. In the next step here, we're going to unnest the weather variables, meaning that we're going to bring them out of that cell and really explode the data frame in the sense that you're going to see all of them in the main level of the data frame, which they're not now, right? So right now, the main level is Daymet all. Right now, all the weather is inside of those cells. We're going to explode those and bring them out of those cells. Whenever we do that, the data coming from the weather column here, inside of it, as we just saw, it has a column for site and one for year. And when we explode them or unnest them, we at the main level of the data set, we also have a column for site and one for year. So those, because you're gonna have those two columns, site and year, are present both at the main level and at the nested level, that's gonna cause us some trouble. So to anticipate that and fix it before it happens, we're gonna come back here to the Daymet all chunk. Right after when you close the parentheses of the download Daymet, so right on this parenthesis here, that is matching that one, just give it a pipe. And we're going to rename those columns. So we're gonna rename, I want the year column. So I'm renaming the ones on the NASA data frame, right? So I want that year column on the NASA data frame to be called dot year instead of year. So I'm gonna say dot year equals to year. The way, if you remember this works, is the first name you give is the new name, and the second name you give is the current name. So I want the current name year to become dot year. And let's just give it a comma here and do the same for sites. So I want dot site to be the new name of the current site. All right, if we do this, let's just run that again. It just downloaded the data for the first 5 locations. And if we inspect again on the Daymet all $ weather bracket 1, now it has a dot year and a dot site columns instead of site and year. Okay, so we just did a quick renaming there, just so we don't have issues when we unnest the data frame. Okay, so next step here, we're going to do the unnesting and do some wrangling. As you saw earlier, we need to do a pivot wider as well. So we're first going to unnest and then do the pivot wider after that. All right, so if you come to this chunk here, I'm calling this Daymet underscore all underscore unnest. So you can just give it the assignment symbol there. We're going to start off with the nested data frame we just created above, which is called Daymet underscore all. Gonna give it a pipe, and we're gonna do, there's a function called unnest. And here we're gonna say which column we want to unnest. In the case of Daymet all, we just have one nested column, which is weather. So it's gonna be unnest weather, right? So something to pay attention to. Daymet all right now has 5 rows, again, because we sliced the first 5 rows of that field of data set. So we had only the 5 rows, and then we have this column weather, where inside of each one of these data frames is like 2,555 rows. So when we unnest this, Daymet all unnest should have, in this case here, 2,555 times 5. This is what I'm expecting to happen. So if we run that and then we print it, yeah, so it has like 12,000 rows, right? So now what happened is we still have the variables that were in the original data frame of year, site, lat, long, and strength. But now if you go to the site, we have all those variables that came from unnesting weather, right? Which are dot site, tile, latitude, longitude, altitude, dot year, measurement, and value. Now, the next thing we want to do here is the same as we have done previously to do the pivot wider, right? Because I want to have a column, each one of the weather variables to be in a column. So we're gonna, after that unnest, we're just gonna add a pipe. Let's call again the same as we did before. So pivot wider, where names underscore from is gonna be measurement. So measurement is the current name of the column that I want to pivot. And then values underscore from is going to be equals to value. If we run that, and then we print Daymet all, now we have 1,825 rows. The reason for that is if you do 5 times 365, you get this number of 1,825, where we have weather data on a daily basis for 5 site years. And then each weather variable is going to be a column here. And then lastly, if you imagine, it's going to be kind of a pain when we're trying to model these columns here because they have like double dots and numbers here and there. So I just want to standardize these current names of the columns to something that would be easier for us to refer to when we're plotting, making models, and so on. So what we're going to do here is add a pipe and call, since we did not load the package, we can call the package name and then the function. So the package name is janitor. So janitor : and then clean names is the name of the function. So clean names is just going to standardize all those double dots and all those special characters on the weather side. So basically added like underscore instead of dots, which I think is going to be more useful for us. Okay, so the next step here is for us to export. And again, the reason why we're doing all this is that we want to understand what were the main weather drivers of cotton fiber strength across 700 site years, right? That is the main reason. So now we just pull weather data, in this case for 5 site years. But after we are done with the class, I do want to ask you to do this for all of the site years. So whenever you do for all the site years, then we want to export this to file for a couple of reasons. Every time that you are doing, either you're bringing raw data and doing extensive wrangling before it gets to a shape that you can actually use for modeling, you want to have one script where you bring raw data, do all the processing. At the end, you export the process data, and that's the data that then you bring into a new script. That's going to be the analysis script. So you don't have to be bringing raw data and wrangling every single time. You do that once, you export that data, and then you reuse that clean data for whatever you need down the pipeline. In this case here, I don't want to be pulling 700 site years worth of weather data every time I run this script. So this script I'm showing you is just for pulling the data. Now we're going to export this data as a CSV. And then anytime we want to further work with this data, we work from that CSV instead of calling again the API, right? So we want to have a local copy of that API call in our computer so we can work from that. And we don't rely on internet connection. We don't rely on the server on the Daymet side to be up. And also because then you're not doing used or unnecessary API calls because you just need to make a call once and save that data. So we're going to export that. So I want to export as a CSV. So we would use the function write underscore CSV, where the first argument is the object name. That's going to be the Daymet underscore all. Oops. Got the and then I want to, then we give the path, right? So we open and close quotation marks. I want to do a // to get outside of code. I want to navigate to the data folder, and I want to call this field weather data.csv. So go ahead and run that. Again, right now, you're just exporting weather data for 5 site years. And the reason why we did that is because I did not want to overwhelm your computers and be waiting here for 5 minutes to download weather data for 700 site years. So whenever we're done with class and you go back to your office and you want to take a coffee break before our previous class, just what I do want to ask you to do is to come back to this chunk and just either delete or comment off the slice, right? So keep all the 698 side years. Yes.
Is it Daymet all of the file that we?
The one that you export, oh, yeah. Thank you. Yes, Pramod, it's the unnest. Yeah, sorry, I think I said they met all, right? So please, yeah, make sure that so I initially said to write the they met all. Thanks, Pramod, for noticing this. Actually, I want to export they met all unnest, right? So please make that correction there. And so just again, a reminder, once you go back to your office and you have a moment to spare, I do want to ask you to come back to the chunk where we did the Daymet all, comment off the slice 1 to 5, or maybe just delete that altogether if you wish, and let it run for all 698 side years. I think on my side, when I ran this, it took maybe 5 minutes. I would expect to take about the same time on your side. So it's not going to be a very long coffee break, but I just did not want us to, be waiting here on all of our computers to run for 5 minutes. So make sure you do that. And once you do that, you want to run again Daymet all on nest, and you want to run again the write CSV. So export the weather data for all 698 side years. All right, so a quick summary and some other advice in case you want to explore the open source data side. So today, as a summary, we used year, longitude, and latitude to pull daily weather data from Daymet. We wrote the code to automate that and iterate this process for 698 site years. So again, iteration is something that the more complex data you have, the more just not just in size as far as like how many gigabytes you have, but also the complexity of time and space, the more you will benefit from learning how to iterate and automate things. So this was one exercise for us to flex that muscle. And then we exported this data frame so we can reuse. So in the next class on Thursday, we're going to bring back in the CSV with the weather data for all 698 site years. We're going to do some feature engineering, which is basically creating some new variables from the ones we have. And at that point, we're going to be ready to start modeling. So we're going to start getting to some of the algorithms that's going to lead into machine learning algorithms towards the end of the class. And just to give you some more resources here, so there are really many open source databases that we can pull from. I left you here some of the APIs to some of them. So if you're interested in crop statistics, again, USDA, National Agricultural Statistical Service, NAS for short, has a lot of good resources. I left you here a vignette for a package in R that has an API to USDA NAS. So if you have ever used USDA NAS, most commonly people do that through the browser, where you just make a whole bunch of selections. You can also automate that through R using this package that I'm giving the link right there. For soil properties, I'm giving you here 3 options. One is called Polaris. This is the one that gives you soil properties at 30-meter spatial resolution, which is pretty good. It's probably the smallest spatial resolution you're going to get for soils. But I believe Polaris is just for the US. So if you want to do something outside of the US, you can use Soils Grid, which is at 250 meters spatial resolution. And also within the US, there is Sergo, which is partially what Polaris uses to create its own layers. So just some resources for soil properties. If you're working with soil water, I gave a workshop on how to pull this map data. So this map is, what is it? Soil map active, or I don't remember now, but it is basically a satellite product from NASA as well that gives you an estimate of different soil water content metrics across the US. So I gave you here the link for my workshop if you're working with water. There's also the drought monitor is a really important layer that we get especially for ag, which on a weekly basis, they release the drought condition across the entire US. And you can get this data here as well through an API. For remote sensing, there are many APIs. One I'm leaving here is the one for Planet. So Planet is a satellite company that provides, it's not fully open source. It is free for research. So you can apply for a research license and you can get imagery within certain limits of size and time. But it is open source if you're doing research. So we can get this imagery here. You can get imagery at a daily revisit time. So daily temporal resolution, and the spatial resolution is 3 by 3 meters. So as far as what we can get without having to pay, this is probably the best resource. And then if you're working at the field level, you want elevation data to understand water movement, slope, aspect, those things. I'm giving you here a link for elevation. So you can explore that and how to pull all these open source data, at least most of them, for different purposes. All right, I think this wraps up the exercise for today. Make sure you save, make sure you stage, commit, and push to your, as you created this as a GitHub project. I guess I did not fully explain this, but for this class, since we're using GitHub and I am asking you to commit and push, you know, if I still have not decided depending on how much time this is going to take me, but I may come to your repos because they're supposed to be public and check if you are properly creating the projects, if you're properly staging, committing, and pushing. So keep that in the back of your mind as we move forward. You want to keep those updated for all projects that we have. And speaking of GitHub, let me take your attendance for today. All right, make sure that you claim your attendance if you're in class. So something that so Ujwal, you actually gave me an idea. So Ujwal was asking me the other day if I had a code that read GitHub issues and created that into an attendance sheet. I did not have until that point, but then I thought, let me look into that. So actually, yeah, I was able to create a code that does automatically the attendance through GitHub. So what I'm going to be doing for this point on is claim your attendance right now. I'm going to close this issue here before we close the class, and you can only claim it attendance if you were here in person when the issue was open. So make sure you claim it. Also, I do want to remind everyone, so today we had a quiz at the beginning of the class. Class starts at 9:30. I do expect you all to be here 9:30. It is fair game for me to have a quiz at 9:30. So if you want to make sure you get points for that, be here on time, as that may happen again in the near future. All right, any questions about anything? All right, I don't hear anything, so thanks everyone, and I'll see you on Thursday.